So in this lecture, I'll prove the existence of a green function. I won't give you all details in this lecture because it would take too much time, but I will give you references. So let me first say that D, a subset of R2, is called a domain if it's an open and connected subset. So we will represent the boundary of D. So delta D will represent the boundary, and the boundary is just the closure of D minus D itself. So this is the definition of the boundary. Now, if I have U a function, so these are definitions. So if I have a U a function which is defined on D and taking real values, I will say that U is harmonic if the following holds. Well, U, it's a function of class C2 in D. This means that at all points of D, U has a second derivative on each directions, and that these second derivatives are continuous. And moreover, the Laplacian of U is equal to 0. Here, Laplacian is a differential operator which is given by, I will be here working in dimension 2 in all this lecture. So in dimension 2, this means that if you take the second derivative in the first direction, which I'm calling x, and if you take the second derivative in the second direction, which I'm calling y, and if you sum these second and first derivative, you get exactly what I'm representing by the Laplacian of U. So saying that U is harmonic is to say, first I need U to be at least 2 times the differentiable, but I will also assume that the second derivative is continuous, and then that the Laplacian of U is equal to 0 at all points of D. So this means that the Laplacian of U, if computed at x, it's equal to 0 for all x in D. So this is the definition of an harmonic function on D. So here is a theorem concerning harmonic functions. And the proof of this theorem, you can find it in the book by Gilberg and Schrödinger. And this theorem, it's called the maximum principle. So assume that D, it's a domain in R2. And assume that we have a function U, which is defined on the closure of D and taking values in R. So I'll assume that U, it's of class C2 in D. So I already defined, and I also assuming that the function is continuous in the closure of D. So U, it's 2 times differentiable on D, and the second derivatives are continuous, and U, it's also continuous on the closure of D. And I'm assuming that U, it's harmonic. So delta U, it's equal to 0 on D. Then what the maximum principle says is that U assumes its maximum and its minimum at the boundary of U. So the result tells you that for all x in D, what I have is that U of x, it's less or equal than the supremum in y in the boundary of D, of U of y, and it's larger than the infimum of U at the boundary of D. So this is the theorem, and you'll find the proof of this theorem in chapter 2 of this book. And one thing that this theorem tells you is that if you consider the following equation, so you want to solve the Laplace equation, which is delta of U, it's equal to 0 on D. So I'm looking for a function which is harmonic on D and which is equal to a given function at the boundary of D. So I'm fixing a function f, which is defined at the boundary of D, and say that, let's say that f is continuous, if you wish. And now I'm looking for a function u, which is of class C2, so that the Laplacian of u makes sense. So it's of class C2 in D, and which is continuous in the closure of D. So it follows from the maximum principle that this equation, if it has a solution, I'm not claiming it has a solution, but if it has a solution, this solution is unique. So there is at most one solution, and this simply because assume that you have, so let me give a proof of this, which is elementary. So assume that you have two solutions, which I'm representing by u1 and u2. Then if I define v to be the difference of u1 minus u2, from the first equation by linearity you get that dv is equal to 0. And from the second equation, you get that v is equal to 0 at the boundary. Now you have a function v, which is in C2 D intersection C closure of D, which is harmonic on D. And therefore, by the maximum principle, you know that the maximum value of u and the minimum value of u is attained at the boundary, so that v of x it's bounded by the supremum at the boundary, but the supremum at the boundary is 0. And u of x, it's also bounded below by the infimum of v, but the infimum of v at the boundary is 0, because v is identically equal to 0. And from this, you get that from the maximum principle, you get that v is equal to 0. And this, therefore, gives you that there is at most one solution for the Laplace equation which is this equation. Now let me give you the definition of a green function. So I'm fixing D, a domain in R2, and I'm fixing a point which I'm calling x0, x0 in D. I will say that a function g, which depends on this point x0, from the closure of D to R, is a green function if the following conditions are matched. The first one is that I want to write g x0 of y as a smooth function, which I will represent by k x0 y, minus a function which has a singularity at x0. So this function, and which is harmonic outside x0. So I want g to be a smooth function minus a function which has a singularity at x0. Why I'm taking here log of y minus x0 is for the following reason. If you take y different from x0 and you compute the derivatives of this function, you realize that this function is harmonic. So this function is harmonic at any point y different from x0, but at x0 it has a singularity of logarithmic type, and therefore what this first condition is saying is that, well, you can write the green function as a smooth function minus a function which has a logarithmic singularity at x0. Now, second condition will impose g to be equal to 0 at the boundary of D. For g to be 0 at the boundary, this is the same thing as requiring k to be equal to log at the boundary. So the second condition states that k x0 y it's equal to log y minus x0 for y at the boundary. And the last condition will require k x0 to be harmonic in D and to be continuous up to the boundary. So I want k x0 to belong, well, it has to be continuous up to the boundary. It has to be of class C2 on D. And I want it to be harmonic. On D. So in particular, if you look at the definition of G, this means that G is harmonic because it's the difference of two harmonic functions at D except at the point x0 where the second function has a singularity at x0. And so what I want to prove in this lecture is that whatever bounded domain D in R2 whose boundary is smooth, we can define a green function for that domain. So before proving the theorem, let me state another theorem which shows the interest in proving the existence of a green function. So let D be a bounded domain and let's assume that there exists a green function, and I will assume, so the green function, remember, we require it to be C2 up to the boundary, and C2 in the domain, the domain D. And to be continuous up to the boundary, well, I'll assume it to be C1. And I will assume, well, I will assume no, but let me assume, yes, that B, the boundary of the domain to be smooth. So that at each point I can define a tangent plane and I can define a vector which is a unit vector, which I'm calling, so I'm taking here point Z in the boundary of D, and N of Z will be a vector which is orthogonal to the tangent plane, pointing outward, so here's the domain D, so it's pointing outward, and it has norm equal to 1. So this is this vector N, which is defined at the boundary. And let me say that f, now it's a continuous function defined at the boundary. Let me define u of x to be, or u of x0, to be the integral over the boundary, b, of f of z. And now since g of x0, it's assumed to be a C1, I can, up to the boundary, I can take its derivative, gx, with respect to this unit vector n. And now I can integrate it over this one-dimensional surface, which is the boundary of D, and let me represent by sigma dz, the measure at the surface. So this is computed at z. So let me repeat. I'm representing the boundary of D by B. I'm assuming that this boundary is smooth enough so that I can, at each point, define the tangent plane at that point. And then I'm defining this unit vector, which is pointing outward and which is orthogonal to the tangent plane. And I'm assuming that for all x0 in D, I can define a green function, gx0. And I'm assuming that this green function, it's C2 as before on D, but now instead of assuming that it's continuous up to the boundary, let me assume that it's C1 up to the boundary so that I can define the derivative of G with respect to n at the boundary. And for this, I need some regularity. I need it to be C1. So if this is the case, now for any function f defined at the boundary and continuous, let me define u of x0 by this integral. Then what I can prove is that u is the solution of the Laplace equation with boundary value given by b. So the Laplacian of u, it's equal to 0 on D, and that u, it's equal to f at the boundary of D, which I'm calling b. So it follows from the existence of a green function that you can solve the Laplace equation for any continuous function, and you see that for that I need only f. For this integral to be well defined, I only need f to be bounded. So actually, we can prove the existence of a solution of Laplace equation with any measurable bounded condition f, provided that the green function is of class C1D in the closure of D. So this is why green functions are important, and we will present now a proof of the existence of a green function. So here's the theorem which we want to prove, is that let's assume that D, it's a bounded domain. Of R2. And let's assume that the boundary, and let me call B the boundary of this domain, let's assume that it's smooth, so it's C1, which means that at any point of the boundary, well, the boundary can be approximated in a region by a C1 function. And then what I claim is that for all x0 in D, there exists a green function which I will represent by g x0. And the proof which I will present, it's due to Lax, and it's based, as you will see, on the Hahn-Banach extension theorem. So I have my domain, bounded domain here D, with a boundary given by, represented by B, and I want to prove the existence of a green function at gx0. Well, let me define as x the space of continuous function defined at the boundary of D, which is, in my notation, C of B. So this is a Banach space endowed with the L infinity norm. Now I will define a subspace of X, which I will be representing by Y. And Y is the set of functions f in X, so the functions which are continuous, for which there exists a solution to the problem, to the Laplace equation, which is delta u is equal to 0 on D, and u equal to f at the boundary, which I'm representing by B. So Y is the set of functions f in X, so the functions, the continuous functions defined at the boundary, for which this equation has a solution. So I have several observations. First, the set Y is non-empty. If you take f equal to a constant, then you see that u equal to this constant is certainly a solution for this equation. The Laplacian of a constant is 0, and the function is equal to the constant at the boundary. So y has at least the constant functions inside of it. Then, well, let me just specify here that what I mean by a solution to this equation is what I meant before, which means that I require u to be in C2 d intersection C closure of d, that the Laplacian of u to be equal to 0 on d, and u equal to f on. So it's implicit in this requirement that I'm assuming that u is continuous up to the boundary and that it's C2 at d. So why it's non-empty? First, then second, u, by the maximum principle, u is well defined. So there is, if there is a solution, there is only one solution. And this has been observed before and follows from the maximum principle. And therefore, I will represent this solution by uf. So if f belongs to y, which means that if this equation has a solution, then I will represent by uf the unique solution. And the third observation is that u is linear. So to prove that u is linear, let's take two functions f and g in y. Since f and g belongs to y, this means that this equation with f and g at the boundary have a solution. There is at most a solution, so I'm representing by uf and ug the solutions of these equations with the boundary f and the boundary g. So it's easy to see that uf plus ug is a solution of this equation if I replace f by f plus g. Indeed, uf and ug are harmonic, so this equation is satisfied on D. And at the boundary, uf plus ug is equal to f plus g. Therefore, if f and g belong to y, uf plus ug is a solution of this equation with f plus g. So this means that f plus g belongs to y, and uf plus g it's equal to uf plus ug. So this proves that y is closed by addition, and the same argument shows that y is closed by multiplication by scalars. So y it's indeed a linear subspace of x. So I defined x, I defined y. Now we'll define a bounded linear function on y. So let me take a function f in y. So this means that there exists a solution uf of the Laplace equation. Lx0 of f will be the value of the solution at the point x0. So this formally Lx0 at f, it's equal to ux0 uf at x0. So you fix a function, a continuous function defined on the boundary. Since it belongs to y, this means that this equation has a unique solution. It has a solution, and we know that this solution is unique. So Lx0, it's giving me the value of this solution at x0. So this is the definition of this functional. I claim that Lx0, it's bounded and linear. So let's prove that it's linear. So let me take a sum of f plus g, assuming that f and g belong to y. So this, by definition, it's uf plus g at x0, but we have seen that uf plus g is equal to uf plus ug. So this is uf at x0 plus ug at x0, and this is exactly Lx0 at f plus Lx0 at g. So indeed, Lx0 applied to the sum, it's equal to the sum of the Lx0. And if you multiply a function by a scalar, the same computation will show you that, will give you that Lx0 is linear. So now let me prove that Lx0 is bounded. So I want a bound on Lx0 of f. But this, by definition of Lx0, it's equal to ux0. I'm always mixing my notation. This is uf at x0. But now you know by the maximum principle that uf at x0, it's less or equal than the supremum for z at the boundary of fz, and it's bounded below by the infimum of fz for z in the boundary. And it follows from these two inequalities that the L infinity norm of u, it's bounded by the L infinity norm of f. Mind that here I'm taking the L infinity norm of u on the closure of D, and here I'm taking the L infinity norm on the boundary of D. This inequality gives you this inequality for x0 in D, but at the boundary, u is equal to f, so this inequality at the boundary, it's trivial. So we get from the maximum principle that the value at x0 of uf, of the solution of the Laplace equation with boundary value given by f, that this is bounded by the L infinity norm of f. And so this inequality is telling me that indeed Lx0 is bounded and that its norm is actually bounded by 1. Well, I claim that the norm of Lx0 is actually equal to 1 because if you take Lx0, we've seen that the constants belong to y, and if you take Lx0 at 1, this is exactly equal to 1 because u1, if you take the solution of the Laplace equation with constant value at the boundary, the solution is just constant. So if you take the boundary value to be 1, the function is constant equal to 1, and therefore Lx0 of 1 it's equal to 1. So mind here, 1 represents a function which is constant equal to 1, while here it's the real number 1. It follows from this identity that the norm of Lx0 it's larger or equal to 1. And since we proved that it's less or equal than 1, with this inequality we get that actually Lx0 is equal to 1. So what I did in these last minutes is I introduced this functional defined on y, and I proved that this functional, which is given by this formula, it's bounded and linear. So we defined Lx0 from y to r by the equation Lx0 of u of f, it's equal to uf at x0. And we have seen that this is a bounded linear functional whose norm is equal to 1. And now we will apply Hahn-Banach theorem to extend this bounded linear functional to the whole space X. So Hahn-Banach tells me that there exists a linear functional which I will represent by capital L from X to R. So this is a bounded linear functional, and its norm, it's equal to the norm of L, so this is 1. And Lx0, it's an extension of small l x0, so if I apply that to a function f in y, Lx0 of y, it's equal to Lx0 of f, and this is uf x0. So now what I will do is I'll present some properties of this bounded linear function Lx0, which is defined on the space of continuous functions at the boundary. Now I want to define a class of functions defined at the boundary of D. So for each y in R2 minus B, I will define a function hy, which is defined on B and take values on R. And actually, you'll see that hy, it's an element of Cx. Of x, of Cb, which is x. So let me define hy. Hy will be given at z. So z, it's an element of the boundary. Hy will be given by the logarithm of z minus y. Since y does not belong to B, y can be either an exterior point or an interior point. And you see that if it's an exterior point or if it's an interior point, the function, since there is a positive distance from y to the boundary, in both cases, this function is a continuous function, and therefore it indeed belongs to x. Now, I want to obtain some properties of hy if y does not belong to the closure of D. So assume that y does not belong to the closure of D. And what I claim is that in this case, hy actually belongs to y. So let's prove that. To prove that, let me denote by my. Now, this is a function defined on D bar and taking values on R. And my of omega of w, it's equal to the logarithm of y minus w. A simple computation, since y it's an exterior point, shows that my, it's a continuous function up to the boundary, and it's a smooth function, so in particular it's a C2 function on D. You fixed y an exterior point. Now you look at the function log w minus y inside D, and you get that, well, this function is smooth, and it's also continuous up to the boundary. And also, if you compute, a simple computation shows that my, it's harmonic on D, and that my and hy coincide on B. So this shows that my is the solution of the Laplace equation. dmy, it's equal to 0 on D, and my, it's equal to hy on B. So we just proved that if ay does not belong to the closure of D, the Laplace equation has a solution, and this means that hy indeed belongs to the space Y. Also, it gives you more than that. Remember that we represented by h of y the solution of the Laplace equation. Here we know exactly what the solution of the Laplace equation is. This is my, which is the function given here. So I will define k x0 of y for y outside D as Lx0 of hy. But since I'm assuming here that y does not belong to the closure of D, hy, we just seen, belongs to y. And therefore, since Lx0 is an extension, this is actually Lx0 of hy. Now, by definition of small l at x0, this is u at hy x0. But we know that u hy is equal to my, so this is my at x0. And my, we have an explicit formula, so actually this is log of y minus x0. So with this definition, we proved that k x0y is equal to the log of y minus x0 when y does not belong to the closure of D. So the important definition is this one, and this computation shows that k x0 of y is equal to the log of y minus x0 if y does not belong to D, the closure of D. So in the previous case, I considered a case in which, in the previous take, I considered a case in which y does not belong to the closure of D. Now, consider the case in which y belongs to D. I will define k x0 of y in the following way. We have seen that hy belongs to x. So I can Lx0 of hy. It's well defined because hy, it's a continuous function at the boundary if y belongs to D. So this object here, it's well defined. We don't know exactly what it is, but Hahn-Banach theorem guarantees that this bounded linear function will exist, and therefore that this makes sense. And so for y in D, I will define k x0 as Lx0 of hy. So this is exactly the same definition I presented for y out not belonging to the boundary of D, to the closure of D. So this defines k x0 in everywhere but at the boundary. So let me extend the definition of k x0 by stating that it's equal to the log of y minus x0 if y belongs to the boundary. So now I have a full definition of this function k x0. If y belongs to the boundary, it's given by this formula, while if y does not belong to the boundary, it's given by this equation. And we can decompose in two cases. If y does not belong to the boundary of D, this is, we have seen, log x0 minus y. While if y belongs to D, well, we don't know exactly what it is, so I'll keep the formula Lx0y. And this just to tell you, to show you that this function k x0y, it's continuous out of D. So we have same definition for y in the boundary and y out of the closure. So if we consider the function k x0 outside D, we have a continuous function. It's given by these quantities. Now, what I want to prove is that this function k x0 has exactly all the properties required in the definition of a green function. So this is what's to come. So in the previous take, we introduced this function k x0, which is equal to log of y minus x0 if y does not belong to D. And while if y belongs to D, it's given by Lx0 applied to hy, where hy is this continuous function defined at the boundary. And now I want to introduce g, I can finally define g. So here is the definition of g. gx0 at y will be given by kx0 y minus the log of y minus x0. And we want to prove that jx0 is indeed a green function. So in order to prove that jx0 is a green function, what we need to show is that kx0 at the boundary of D is given by the log of y minus x0, but this is indeed the case because if outside D, so in particular at the boundary of D, the function k is defined by log of y minus x0, so this property here, it's automatically, well, it's already proved. What remains to be done is to show that kx0 is continuous and it's harmonic on D. So this is my goal now. It's to show that this function is continuous and that this function is harmonic on D. So let me start by proving that kx0 is harmonic on D. And to prove that, I want to compute first the derivative with respect to the first direction of k. So here I'm using y as y1, y2. So y1 and y2 represent the two coordinates of y. And I want to compute the derivative with respect to the first coordinate of kx0. I'm interested in proving that it's harmonic on D. So we will be working with y in D. And for y in D, we have this formula for the function where hy, remember, it's given by that. So this is, the derivative will be the limit as epsilon goes to 0 of kx0 y plus epsilon e1. So v1, it's the first element of the canonical basis of R2 minus kx0 y divided by epsilon. And this is the limit as epsilon goes to 0. So let me just replace kx0 by its definition. So this is 1 over epsilon times L x0 y hy plus epsilon e1. Let me go step by step. Minus L x0 hy. Right. So D, it's an open set, so I'm taking epsilon sufficiently small for y plus epsilon times e1 to be in D also. Now, what this argument will show is that the derivative with respect to D1 commute with the bounded linear functional Lx0. So what we will be proving here is that you can commute these two operators. And well, if this is true, it works also for the second, and therefore the Laplacian, which was out of the bounded linear functional, will be transferred inside the boundary, inside L. And since H, it's an harmonic function, once I introduce inside L the Laplacian, what I will get is that indeed K, it's harmonic. So well, let's do that step by step. So the first observation here is that Lx0 is linear. So I can rewrite this limit as the limit as epsilons go to 0 of Lx0 of hy plus epsilon e1 minus hy divided by epsilon. And I want to now to consider this limit. So you see, L, it's a bounded linear functional. So if I can show that this sequence of continuous functions converge in L infinity to a function, let me represent it by, I don't know, P of y. If the sequence of functions as epsilon goes to 0 converge in L infinity to a continuous function, since L is bounded, what I will get is that this is equal to Lx0 of Py. So what I really have to prove at this point is that this sequence of functions, as continuous function defined on the boundary, converge uniformly to a function P of y. So let's do that, and that will be very simple because we have an explicit formula for the function hy. So hy plus epsilon e1 minus hy, and this divided by 1 over epsilon, it's equal to 1 over epsilon. Let's compute that at a point z, where z belongs to the boundary. And we want to show that this convergence is uniform at the boundary. Well, by definition of hy, this is the logarithm of y plus epsilon e1 minus z minus log of y minus z. And, well, since y belongs to the interior of D, so y is somewhere here, it's clear that this function is differentiable, and it will converge uniformly to its derivative. So this will converge uniformly to the derivative in y of the function log of y minus z, but this is exactly h of y. So we proved, well, we didn't prove, but you can prove that this sequence converges uniformly at the boundary to this function, and therefore that this limit is equal to Lx0 derivative with respect to y1 of hy. And this is exactly, so this is the derivative with respect to y1, and this is exactly what I was claiming here. I was claiming that if you take the derivative 1 of Lx0 of hy, that this is equal to Lx0 dy1 hy. Right? And so this is proved. And once you prove that, what you get is that the Laplacian of kx0 at y, this is the Laplacian of Lx0 of hy, but you can commute the derivatives with the bounded linear function of Lx0. So this is equal to Lx0, the Laplacian of hy. And hy is, and this Laplacian is taken with respect to y. And h of y, since we are taking y on D, at the boundary of D, h of y is harmonic. So this is equal to Lx0 of 0, and L, it's a linear functional, so this is equal to 0. And this proves, therefore, that indeed kx0, it's harmonic on D. So this is the first step, the first statement we needed to prove for our function kx0. So to complete the proof, it remains to show that kx0 belongs to, it's continuous up to the boundary. So here, what we are doing, let me make a larger picture. We have here the domain. We have here a point. We know that at this point, kx0, at this point, say z, it's defined as the log of z minus x0. Now we want to show that if I take a sequence of points y in the domain, say, converging to x, so that kx0 y will converge to kx0 of z. Right? We want to show, well, we know already that it's smooth inside D. We want now to prove that it's continuous up to the boundary. So we'll take a sequence y converging to a point z, and we want to show that kx0y converge to kx0 of z. As I pointed out before, we know that outside D, this function is continuous. And here is how Lax proved the continuity, is just by showing that actually kx at y, it's very close to kx at another point, which is also converging to z, but converging from outside. So what it is following, well, consider the closest point at the boundary to y. So there might be two, but if y is very close to the boundary, there will be only one because we assumed the boundary to be smooth. Since the boundary is smooth, I can also define the tangent at this point. So here at this point, it's the closest point to y at the boundary. Once I obtain this point, which is unique if y is close to the boundary, now you can take the tangent, because I assume the boundary to be C1, and define y as the reflected point. So y bar will be the reflection of y through this tangent. And since y is converging to z, also y bar it's converging to z. Out of the function kx it's continuous. So to prove that kx is continuous coming from inside the boundary, it's enough to show that the limit as y converge to z of kx0 y minus kx0 y bar, that this is equal to 0. Okay? So this is Lax's idea. So in order to prove that you are continuous from inside, since we know that it's continuous from outside, let me compare the value of k at these 2 points. And if I can show that as y converges to z, the difference converges to 0, we know that k is continuous from the inside because k is continuous from the outside. So this is what we need to prove. So let's see what this is. I want to take y to z. So z is a point at the boundary, and I want to show that these limits occur. But by definition, kx0, it's lx0 of hy minus, and this is lx0 at hy bar. So let me erase this picture. Again, by linearity, this is the limit of y converging to z of lx0 of hy minus hy bar. So these are two functions, hy and hy bar, are functions defined on the boundary which are continuous. And again, if I want to prove that this converges to 0, I can use the continuity of lx0 to show that it's enough to prove that hy minus hy bar converge to 0. Right? If these are continuous functions defined at the boundary, if this difference in the L infinity norm converge to 0, then I can use the boundedness of this operator to show that this absolute value goes to 0. So what I really need to do is to prove this convergence. But this convergence means that I'm taking the supremum over all points at the boundary. So let me say, since I used already z, let me take w at the boundary, supremum of the L infinity norm. Now I know exactly what h is. So this is log of y minus w minus the log of y bar minus w. Well, this is equal to the supremum for w in B of the absolute value of log of y minus w divided by y minus w. So I want to prove that this limit, this supremum, converges to 0 as y converges to z. So let me draw again the picture. Here is z, here is w, here is the tangent plane, so here is w bar, and what I have here is the log of, so I'm considering here point w, and I'm taking the log of w minus y, comparing that to the log of w minus y bar, and as y converges to 0, to z, I want to show that this ratio converges to 0. But to prove that this ratio converges to 0, what I really need to show is that this ratio converges to 1. So it's enough to prove that the supremum for y in B of y minus w divided by y bar minus w, that is converges to 0 as y converges to z. And now, well, this is a computation which I will omit, or I will leave it to you as an exercise to prove that this is indeed the case. And it's not 0, I'm sorry, here it's 1. And if you want to find the details of this computation, you can look at the book by Lax, Functional Analysis, or a book by Martin Davis, which is called a first course in functional analysis, which gives you all the details of this proof. It's not too long, but not too short to present it here in this lecture. But say that once you prove that, you have shown that k, it's a continuous function up to the boundary, and therefore that the function g, which I introduced, it's really a green function. And this proves, therefore, that the existence of a green function provided D, it's a bounded domain with a smooth boundary. Let me say that this proof, it's really brilliant. It shows all the ability of Peter Lax. I'm really impressed by this proof.